So about the two accelerators, so we are in the unique situation at University of Mainz that we have an existing normal conducting accelerator and now are in the process of constructing a new one, a superconducting accelerator MESA, and I will give you some overview about how MAMI and MESA are located in our building, and I will give you some accelerator basics, why we need accelerators, why we especially Electron Linux, and how do they accelerate particles, and at the end also about the special kinds of accelerators we have here named microtrons and energy recovery Linux. And at the end I will show you the MAMI accelerator, some sheets on this, but you will visit it starting in half an hour, I think. And afterwards I will give you an overview about the MESA accelerators. For the MESA accelerator, as it is under construction, I have some more sheets in order to show you what we are going to build, and I will finish with a summary and an outlook. So at University of Mainz we have since more than 25 years we have a microtron cascade operating. So this is called MAMI, the Mainz microtron, and you can see here it's starting from small and getting bigger and bigger, and at the end serving two experiments. In 2012 we succeeded in getting a cluster of excellence funded, and so we proposed a new accelerator project, which is the Mainz Energy Recovery Superconducting Accelerator. And I will talk to you what means energy recovery and also what means superconducting. This should have been built here in this given up experimental beamline, and some years later we extended our experimental hall, so we granted for a research building because the space for the dedicated experiments of MESA was growing and growing, and so we extended the hall, so it will be an underground hall will be ejected here, and then everything is fine for MESA. So we have this running machine which we can visit at the moment. We can also see the spectrometer and the A2 facility, and we have this part under construction. There we cannot see any hardware, but I will show you some pictures. So now to the motivation, accelerator basics, why we need high energies of particles for research. And if you go to this optical limit, I think it's called the AB limit, then you might know that the size of an object you want to investigate cannot, if you want to resolute something, it has to be in the same order of magnitude like the light you are using. So half of the wavelengths of the light you're investigating an object, smaller structures you cannot see. And as light is in the hundreds of nanometers range, you cannot see any atoms using light. So you need to go to higher energies, and for example, Ernest Rutherford, he had a natural accelerator. He had a radioactive isotope emitting helium particles or alpha particles at a given energy, and using this he discovered that we have a nucleus inside of every atom. So for investigating smaller and smaller structures, you will later see you need smaller and smaller wavelengths, which corresponds to bigger and bigger energies. So the distance of atoms is in the 10 to the minus 10 range, but the size of one atom is roughly 1 times 10 to the minus 10. And but if you now go to the nucleus, you see the nucleus is 4 orders of magnitude smaller than the atom itself. So inside of an atom there's a nucleus, then roughly nothing, and the electron hull, which is roughly 4 magnitudes away from the nucleus. But this is not the end. So inside of the nucleus we have the nuclei, so protons and neutrons, and some days later it was found out that even proton and nucleon is not a point-like particle, but is consisting of quarks and gluons. So if you want to go to smaller and smaller structures to investigate this, you need higher and higher energies. And here you can see the atoms. You can see atoms by using X-rays, which are in the keV energy range, or you can use electronic microscopes, which are already small accelerators. But if you want to see the nuclei, protons and neutrons, you have to go to the GeV range, and if you want to see quarks, you need several GeV. And in addition, if you want to produce new particles, you have to go to higher and higher energies in order to have enough energy to produce particle-antiparticle pairs of higher and higher masses. So using better microscopes means higher particle momenta. Oh, here you have a mix between German and English, and thus more and more complex accelerators. So sometimes I use this sheet in a German talk, you can see here. So how can you get particles to high momenta? And this the easiest way is just having a high voltage, produce particles and accelerate them. And you can see here the first one of the first accelerators by Walton in Cavendish. Or here you can see a 700 kilovolt terminal as particle source used at the Fermi lab at the US. So the easiest way is just generate a DC voltage and then produce your particles, accelerate them, and you're finished. And this is also the unit. You can see here the unit is GeV, for example. So the unit 1 electron volt means that a particle of the charge of 1 elementary charge or 1 electron has seen an accelerating voltage of 1 volt. And you can see here, if you want to go to giga electron volts, then this would mean you have to produce a DC voltage of more than a billion volt, and this is not possible. You might know why. And so for going to higher and higher energies, you need a different way. But these DC voltages, they are used for example, for small energy accelerators, or also for the injectors of higher energy accelerators. So in this one example is the Van de Graaff accelerator. So here the high voltage is produced by a belt. This is just driven by a motor and transports charges to this sphere here, and this is now connected to the part where the particle source is sitting, and then the particles are accelerated down to here. So these kinds of Van de Graaff accelerators, they can reach megavolts of accelerating voltages, and they are limited by the by voltage breakdown. So at some point, if the voltage is too high, you will have a spark, and then the voltage is low again, so lost. The biggest one was at Daresbury in the UK, and it was a huge device here in this tower, located in this tower, so a vertical accelerator, and it also used a trick. So it was a tandem Van de Graaff. So it started here with negatively charged ions. At the medium energy, they have been stripped to positively charged ions, and then used the same voltage again. So, and it was possible to reach 20 megavolt accelerating voltage or 20 mega electron volt particle beams. But this was the absolute limit, and the limit was given by this. So if you have sparks, then the voltage is gone, and you cannot come to giga electron volts of particle momenta or particle energies. So
if you do that in vacuum, you could.
Yeah, but even in vacuum, you have a breakdown voltage. It's some kilovolt per millimeter, and there are, for example, if you use sulfur hexafluoride as protecting gas, it's even better than in vacuum, but it's only enhancing by a factor of roughly 4 the breakdown voltage. So now the idea how to reach higher energies was not using DC voltage, but alternating voltage or AC voltage. So if you produce particles and they are traveling through this drift tube, and then you have a accelerating field here, then the particles can be accelerated. For example, if your accelerating voltage is 25 kilovolt, then you have 25 keV after this first gap. And now the particles are protected in this drift tube again, and during the time they are drifting through, the voltage is just, the sign of the voltage is changed, and you can accelerate again. And then you can do it a third time, and you can, so using this, you can use your voltage, for example, 3 times. And in principle, you have no more limits for energy now, because you can do it again and again and again, and as long as your funding is not is not running out for tunnels and accelerating structures. Yeah, so this, for example, maybe you have heard of the International Linear Collider. People are discussing about, so that this would be a 30-kilometer collider for electrons and positrons, and it's very, very expensive. So for electrons, you use a little different part here, so you don't use these drift tubes. These are used for heavy ions, for example, at GSI, close to here at Darmstadt. For electrons, you use the fact that they are very quickly roughly at speed of light. So every electron is at the same velocity when it's at roughly 5 MeV of kinetic energy. And then you can use these kind of resonators, so standing wave resonators. And while the electron is traveling from cell to cell, again the sign of the accelerating wave is changing. So the electrons are surfing on the accelerating fields through this RF structure. And so this. But doing so, this means 2 things. So the first thing is that you cannot have a continuous beam anymore, because if you have electron at the wrong phase of the accelerating voltage, they are decelerated instead of accelerated. And so you need to have short bunches of beams. But you can have in every other cell of this accelerating structure, you can have an electron bunch. This is then, if you use every other cell, so every possible position for electrons, then it's called not DC anymore, but a continuous wave accelerator, so producing particles all the time. So now these kinds of resonators, they do not give you the power to the beam for free, and because they are. If you have some electrical fields here which are alternating, you have mirror currents and magnetic fields around the electric fields, and so induced mirror currents, and you have losses. So the losses of an accelerating structure is given by or is related to the quality factor, and the quality factor is 2 pi times the stored energy in the resonator divided by the dissipated energy per period. So if you have a very high quality factor, this would mean, for example, for a pendulum, this would mean it would swing forth and back without getting pushed again for a very, very long time. And the quality factor now, so the details are, you have to visit a lecture about accelerator physics, but you can break it down to this formula. So the quality factor is given by some geometrical factors of the accelerating shape and the surface resistance. And so it's only dependent of geometry and the surface resistivity, but the RF field generate losses. And the dissipated power now is given by the accelerating voltage squared, so double the accelerating voltage. Here I have 4 times the losses. And here are some geometric factors and the surface resistivity. And so the accelerating fields, these are the demands you put on your accelerator. If you want high energies, you want high accelerating fields. The cavity geometry is given by the frequency you want to operate, for example. And the material, operating temperature and frequency, quality of the surface, this is all in the surface resistivity of your accelerator. And so this also gives you the motivation for using superconducting cavities. So on the next sheet you just see a calculation example. If you are running a 1.5 gigahertz pillbox cavity, so a pillbox cavity is just a cylinder. Real cavities are shaped a little bit different, but this is easiest to operate or to calculate. Then you can calculate the 2 geometrical factors, and now you can put 2 different types of materials. The one is normal conducting copper, so the surface resistivity of copper is roughly milliohm at the frequency of 1.5 gigahertz. Or you can use superconducting niobium, which has 10 nano-ohm. And the quality factors now are here in the 10,000s for copper and in the 10 to the 10 of at niobium. So, and this is directly going into the dissipated voltage. So here you would have 190 or roughly 200 kilowatts of dissipated voltage in this cavity. So this is far too much, and you will have much less in a superconducting cavity. But you have to be honest, superconductivity needs is a complicated technology and also needs cooling to cryogenic temperatures, in this case to 1.8 Kelvin, so very cold. But the difference is huge, and the accelerating field of such a device would be 10 megavolt per meter. So what you can learn from this is that you cannot operate a normal conducting device at 10 megavolt per meter. But if you go to 1 megavolt per meter, for example, you are already a factor of 100 lower in dissipated power. And this you can do. And this is the idea of the microtron, the normal conducting microtron as we have it here at Mainz. So you go down in accelerating voltage, but then use the accelerating, use the accelerator, the LINAC, again and again. So you can see here you inject with some energy, send the beam through here, and it is bent back by these huge magnets, comes back here, is accelerated again, has a higher energy and thus a higher bending radius, and you do it again and again until your magnet is the size of your magnet is reached. And so this is very convenient for using the accelerator many times and saving power instead of having one very long LINAC. And here the particles are on the accelerating wave. Yeah.
Can you lose energy when it's turning around? The synchrotron radiation?
Yeah, at the beginning of MAMI you don't lose energy by a synchrotron radiation, but later in the highest steps you have some losses. So but they are not very high because the energy is not yet very high. But it's an effect you can see at the highest energies.
Sorry, so related to that, can you give us a
Oh, it's very different. It depends on the energy. You will see it in some minutes when we visit MAMI. So it starts with a linac in this length and a magnet in this size, and it ends in a magnet which is 450 tons and huge. In huge dimensions, so roughly 10 times 4 times 5 meters, so a huge block of iron. You will see some pictures and also in reality soon. So now a different possibility now for which is used at MESA, or will be used at MESA, is now if you produce a beam with a very high beam current and put it on an experiment and then you dump it, then all the energy inside of the beam is lost, and you need to give these electrons very much energy, and the energy is given by the charge times the accelerating voltage, or the accelerating so given by the beam current times the accelerating voltage. So it's and it can be very, very much. For example, if you operate magics at MESA, you will have at 10 milliamps of beam current, you will have 1 megawatt of beam power at the position of the experiment. And if you now dump it, then all of this power is lost. So MESA will use an idea which has also already formulated in the 1960s, but it is somehow technological challenging. So there are not many types of these accelerators so far. So it's the energy recovery linac. So if you do not destroy your beam completely in your target, so if you have a very thin target, then you can collect the beam after the experiment, all the particles having done only interactions without without giving much energy to the beam or losing much energy, can be collected again and then resent into the accelerating, but now at the decelerating phase. And so you, after using your beam at the experiment, you can decelerate it again and dump it at a much lower energy. So all the energy here, which is decelerated, will be given back to the accelerating fields, and so directly to the next electrons coming for acceleration again. And so virtually this accelerating cavity sees no beam current, and you can gain back your energy and save a lot of RF power. You have the numbers here. For MESA it will be 95% of the RF power is saved. The 5% remaining power is coming from the injector linac. So this is very, very good, and some accelerators are operating as already in this kind of operation, but it's very challenging because now you overlay different particle beams here. One is accelerating, one is decelerating, and you have the phasing has to be very correct and everything else. So it's not very easy. The idea is not so new, but the realization is still on the way. So no one so far has done this in more than one turn. So accelerating, for example, 3 or 4 turns and then decelerating 3 or 4 turns, which already has been successful, is accelerating 1 time, decelerating 1 time, and dump the beam.
So, but why do you have to dump this beam at the end? Why can't you use it for the next round?
Okay, this is because the beam quality is getting worse by every time you cross the target. So using the beam again and again would be a storage ring. So in a synchrotron, for example, you can store like LHC at CERN, can store your particles, and they are circulating all time, or several hours in this case, and doing the collisions again and again. But if you now have a target which disturbs your beam too much, then the beam quality is getting worse every turn. And So this energy recovery linac is a compromise in between a target which has some more influence on the beam, but it's not too harmful in one turn. So you have a higher luminosity here, using the beam only one time, and you always have the best beam quality because you always have a fresh beam at the target. So this is the idea, but it is somehow challenging. So now I will show you MAMI again. So MAMI now here is operating with bigger and bigger microtrons. So the first one has only 8 turns, then you have 50 turns, and in here you have 90 turns. So it's getting bigger and bigger, and the energy is also getting bigger and bigger. So you start with roughly 10 MeV here, 180 MeV here, 850 MeV here, and the biggest one here is bringing the beam to 1.5 GeV. So as the magnetic fields are limited from iron-dominated magnets, the magnets have to grow all the time. And this is the biggest racetrack microtron. So we will visit this in a minute. This is the newest stage of MAMI, which is using a slightly different kind of way of separating and recombining the beam. And here you will see the spectrometers. We will visit everything in a minute, so you don't have to to remember on the pictures. So we have 2 main experiments. The first one is an electron scattering experiment with 3 spectrometers. So the A1 facility with a very, very high resolution of detecting energy and time of flight of the scattered targets, so that you can really do precision experiments at this facility. And the other one is the A2 experiment. So here we first produce a photon beam from Bremsstrahlung. So we do not use the electrons, but we send the photons to the experiment, and here we have a roughly 4 pi detector set up, and we can do experiment inside. So you will see this in a minute. And our new accelerator now will be MESA. So it will be a smaller accelerator, but with a very, very high intensity. So a factor of 10 less energy than MAMI, but at the same moment a factor of 10 to 200 more beam current. So we're in the much higher intensity at the position of the experiment. You can see it here. It consists of a normal conducting injector, and then we have 2 cryo modules. And if you compare to MAMI here, at MAMI we have these very long linacs, and at MESA we can operate with short linacs, but with a factor of 10 higher accelerating gradient. So we have here we have 25 mega electron volt energy gain per pass through one of these cryo modules. And we can also recirculate and use them more than one time, but not 90 turns, but only up to 3. Here we have the 2 experiments. Maybe Sonja has showed you something about. Okay. So this one is an experiment where we send the external beam, so without energy recovery, and this is used for doing a very, very precise measurement of the electroweak mixing angle. This needs to run roughly 10,000 hours of beam time to get the best statistics. And the other one, the internal experiment here, is a 2 spectrometer experiment, and inside we have a gas target, which is only disturbing the beam very, very in a very small amount. And then afterwards you can see here the beamline is continuing after the experiment and goes back into the accelerator, and then we can decelerate the beam. So here we can operate at very high beam current and at an energy of roughly 100 MeV, and this can be used for measurements on, for example, on the proton radius, for dark photon search, and for astrophysics as well. So this is how the accelerator is working. So from a gun and a low energy beam transport, we accelerate the beam in a pre-accelerator, which is normal conducting. and afterwards inject into the recirculator with the 2 superconducting cryo modules. And the beam now can circulate here up to 3 times, gaining more and more energy, and then either can be sent to the P2 experiment. Here we are limited in beam current because we are not recovering energy, or it can be used to the MAGIX experiment. Here we can gain the energy back from the beam and operate at much higher beam current. So in reality it looks like this. So the normal conducting LINAC is consisting 4 copper cavities, and you can see here you need several meters to come from 100 keV to 5 MeV, and the power is coming from a solid state amplifier operating at the 1.3 gigahertz frequency of the cavities. And this is a prototype cavity which we are investigating at the Helmholtz Institute, so around the corner. In contrary to this, if we use the superconducting cavities, we can use a shorter module than the complete injector LINAC to get more than 5 times of the energy gain. So 2 cavities here, 1 meter each, can give 25 mega electron volt per turn to each electron. So the drawback from superconductivity is always you need the cooling. So these cavities are inside of a cryo module. You have a helium vessel for having the helium at 1.8 Kelvin for cooling. And around you have a liquid nitrogen shield and also the insulating vacuum. So this is challenging from another side. And which is always very interesting at these kind of modules is if they behave like we want. So here we have the specified accelerating voltage for each cavity at 12.5 mega electron volt, and the quality factor we want to reach, and you can do measurements of the quality factor with respect to the accelerating field. And if these curves are above the red dot, everything is okay. And you can see here we are operating at 1.8 Kelvin, so every cavity is very fine. We cannot go with one cavity. We cannot go above 16.5 megavolt per meter, but we do not want anyway, so this is no problem. So now this is the measurement of each cavity just after production, and what is very interesting all the time is if it keeps in this quality after you have built it into the module. So at the beginning you just have a naked cavity, and it's easy to produce a very good cavity. For example, for the European XFEL there have been produced 800 of these types of cavities, but the challenge now is to integrate them into a module and still have a very good quality factor, because every tiny particle of dust on the surface produces losses due to field emission and can destroy your quality factor. So to measure this, we had to put these modules into a test bunker at Helmholtz Institute, and you can see here this is the infrastructure to get liquid helium inside of the module and get the evaporated gas helium out again. So and everything, the measurements are done in a test bunker and to protect people from radiation. And we are very happy that one of these modules, so we have two modules, and one module is behaving very good. So you can here you can see the comparison between the vertical test here, and these diamonds, and the horizontal test. So everything is behaving very well, and so one of these modules we could already accept by the vendor. The other one was indeed very bad, radiating a lot and had much higher losses, so we had to send it back, and it is retreated at the moment and will be back soon, and then when we remeasure it, we hope that everything will be fine. So now to conclude, our new accelerator MESA will be set up in the years 2021 and 2022. But we are already testing and ordering many of the accelerator parts, so we are not doing. We are not only waiting until these dates when the building will be ready. And the injector has been tested in a hall which is now emptied again because the construction starts. And one advantage is that we can in the injector linac we can construct earlier than the building because it's in an old part of the building. And so in fall 2020 we really start setting up MESA. But if everything is finished and running, then you cannot expect having first beam to experiments before 2023. So if you, for example, want to join someday to Uni Mainz, then you can, for example, at your PhD thesis, maybe use the first beam of MESA for your PhD work. So a very exciting period of time at the moment for all the experimental and particle guys. And so I want to thank you for your attention. And we will continue with a guided tour soon. But first you can ask questions if you want.
It actually takes to get that thing up and running, although probably still there's many more details that you saved us. So indeed we have some time for questions to ask to Florian.
Yeah.
So what did you say? This will allow you to measure the mixing angle, you said? Mixing angle?
Yeah. So we for measuring the mixing angle, we do a parity violating experiment. So maybe we have some chalk here. So it's just, you have just, for example, you have a proton here, and you send an electron on the proton, and then this electron is scattered in the electric field of the proton, and you have a counter here. So you measure the amount of protons coming in a certain measuring in a certain angle. If you now have a beam where the spin of the electron is polarized, so either in the forward or backward direction, then you can see that the numbers of scattered electrons is not independent from the electron spin. So you have a parity violation of this process, and so you just have to count particles at a certain angle with respect to the polarization helicity of the incoming electrons. Now this is and the challenge now is that the effect is very, very small. So it's only in the you need to measure asymmetries in the ppb range. So you need a very good statistics, so very, very much electrons coming to this target. And in the experimental setup, you also have a big solenoid around the target. So with a very high magnetic field along the axis. So these targets are boosted here. So all the electrons which are scattered are boosted forward. Then you have the Möller electrons, and all the background particles which have to be collected in a pipe here and transported to the beam dump in order to not to disturb the measurement here too much. So but in principle, it's just calculating how many electrons are scattered, for example, upwards when the helicity is in forward direction with respect to the amount scattered when the helicity is in the backward direction. And this is related to the mixing angle.
Yeah, maybe if you don't mind, I can add a little bit of theory. So, I mean, you see that you have a scattering of charged particles for electromagnetism. Electromagnetism is parity conserving. So the parity violating effect comes from the weak interactions. And what is special here is that this is a low energy probe. So you're probing the weak interactions at very low energy. And whereas, for example, if you do measurements at lab or at the LHC, you're probing the weak interactions at higher energies. So this is a very interesting also consistency check of the standard model. And it requires, as you said, the effect is very small because it's an effect coming from a higher scale. So that's why also the theory calculation has to be very precise, and indeed some of my colleagues also in the theory building are doing exactly those calculations that are needed so that the measurement can be performed. Well, the measurement, you guys sort out that the measurement can be performed with the right accuracy, but then in order to connect it, the number that you get that is measured there to the weak mixing angle, you also need the very precise theory computation. So it's very interesting. I think it's very great that everything is really done 200 meters from there are the theorists and the experimenters.
Yeah, you need a very close collaboration between the accelerator people like me to the experiments and to the theory, because so my task in this experiment is to have a very defined property of the incoming electrons, and this for a very, very long time, a very stable, precise, and also long time stability is an issue. So this is very challenging for the accelerator itself. Then the experiment itself is also very challenging for the particle physicists, and the theory again. So, and this all the work is done together in this cluster of excellence. Yeah, at Magix, we will have a beam of electrons. So many electrons coming to this target, and this target now is a gas jet of many protons. So they are so you have a nozzle here and a collector here. So you have a real gas jet going through the beam line. And now most of the electrons are doing no interaction, because as you know, the factor of 10,000 of the atom, there's nothing. And so they are too far away from the nucleus to get scattered. But some of them are doing an interaction here and are scattered to some solid angle, and this can be detected by the spectrometers. But what is disturbing are all the particles which are not scattered to big angles, but to the small angles here, and which are then flying close to the beam, but so very close to the beam, but might have lost some energy and are also scattered to some size. So the beam forms some halo of particles, which later can be lost and can irradiate parts of the beam pipe. So all these small angle scattering here, this is very concerning. And if you have a very thin target, then you have two main benefits from this. The first one is that also for the experiment, it's very, very unlikely that any electron is doing more than one scattering process, because the target is very thin, so the multiple scattering is not an issue. And in addition, you don't have too much halo particles here. So, and then it's always, you always have to, always have to calculate against. So if you have more density of the target, you have a better statistics at the experiment, but more scattering effects on the beam. And otherwise, if you reduce target density, then you have no luminosity and need to measure very long time. So it's you always have to calculate these two things against. So this is the reason why we want to use the ERL beam, because then we have many electrons, so high beam current and a very thin target with a very precise probe at the experiment. But it's also building this kind of target is very challenging, because here you have vacuum, so the beam is flying inside of a vacuum, and here you want to shoot a gas jet through vacuum, so the vacuum is getting worse by shooting gas through. Most of this can be collected here, because if the speed of the gas jet is high enough, then most will fly directly into the pump. But indeed, you will have some effects on the beam vacuum as well. And then you need huge pumps to get all the protons which are now flying here and here and here, to get them away again, because otherwise the electrons will scatter on them as well.